got some fresh images of 3I Atlas, a third ever interstellar object. Now astronomers have captured that moment live, streaming in real time.
June 18, 2025. NASA's live feed, which for hours had been calmly tracking the path of a lone interstellar traveler, suddenly vanishes from public view. 1 second, the Comet 3I/ATLAS is there, drifting against the backdrop of stars. The next, the screen flickers once and then goes black. But not before one final image slips through. A single frame carrying with it the kind of anomaly that ignites controversy for years. In that frozen moment, something glints against the void, a razor-straight edge about 37 pixels long. It lasts only seconds, but long enough to seed one of the most hotly debated mysteries in recent astronomy. Was it fracture, glitch, or design? The final frame. The final frame carried a precise timestamp, 03/1712 UTC. Time markers in space data are not guesses. They are exact digital fingerprints, logged by synchronized atomic clocks and mirrored across multiple systems. That's what makes this moment so jarring. At that time code, every archive shows the same thing: the comet's dim nucleus, cloaked in a fog of dust and gas. All of it routine, all of it expected, until you reach the lower quadrant of the image. There, geometry intrudes. The coma is all softness, irregular wisps, blurred gradients, organic disorder. But cutting across it is a line that doesn't belong. 37 pixels, nearly perfect in their straightness, brightened not by scatter, but by reflection. It is the kind of precision nature rarely produces in a dust cloud. Independent astronomers wasted no time running edge detection software across the frame. Within hours, algorithms confirmed what the eye already suspected. The feature was unusually crisp, far sharper than the surrounding environment. This was not the irregular glow of cosmic noise, nor the jagged streak of dust particles caught in motion. It was something else. Scientists broke the light down into its component bands, looking for clues about what had reflected it. The result was tantalizing: a clear spike in visible wavelengths, coupled with a secondary peak in the near-infrared. Under laboratory conditions, such a profile often suggests polished alloys. But the same shape could, under rare conditions, emerge from silicate minerals, ordinary, natural rock. The problem was not the data. The problem was that both answers fit. Was the glint nothing more than sunlight bouncing off a freshly fractured face of ice? Was it a cosmic ray artifact, amplified by the feed's compression? Or was it something engineered, a smooth surface that no comet should carry? Verified evidence trail. In the minutes after the blackout, while NASA's official feed hung in silence, a parallel story unfolded. All over the world, citizen archivists had been quietly running their own scripts, capturing raw data packets the moment they were broadcast. It's a community of hobbyists and researchers that most people don't even know exists. On that June night, archivists in Australia, Germany, and the United States caught the anomaly. Each of them independently uploaded their packet captures within minutes. To prove authenticity, they generated cryptographic hashes, long, unique strings of numbers and letters that act as digital fingerprints. The logic is simple. If even a single pixel changes, the hash breaks. The result? Every hash aligned perfectly. The file from Germany matched the one in Australia. The one in Australia matched the copy stored by a retired network engineer in Ohio. Bit for bit, pixel for pixel, the files were identical. No tampering, no alteration. The anomaly was locked into the record. This chain of custody is what gives the event its staying power. It isn't just that NASA captured the frame, it's that dozens of mirrors, independent and decentralized, carried the same evidence. Data copies were uploaded to academic servers, seeded across encrypted torrents, even written into blockchain-based timestamping services. Anyone, anywhere, can download them and verify the integrity for themselves. The first mirrored copy appeared on a German university server at 3:21:07 UTC, less than 5 minutes after the blackout. An Australian science node followed seconds later. Each upload included not only the raw file, but also its size, its checksum, and a direct link back to NASA's original relay. Within the hour, astronomy forums were buzzing, sharing download links, encouraging others to run their own verifications. This level of forensic transparency is rare in science. Usually, when anomalies appear, debates rage over whether the data was altered, corrupted, or misinterpreted. In this case, the evidence trail is airtight. The anomaly is there in every copy, captured at the exact same timestamp, preserved across continents. That makes it immune to the usual criticisms. Whatever the anomaly is, fracture, glitch, or something designed, it cannot be dismissed as fake. One frame, mirrored across the globe, preserved with mathematical certainty. An anomaly too crisp to ignore, and a blackout that followed too quickly to dismiss. Forensic pixel analysis. Once the final frame was secured and verified, the next step was to pull it apart, pixel by pixel. Digital forensics thrives on details invisible to the casual eye, and this case demanded nothing less. NASA's live feeds, like most high-bandwidth space transmissions, rely on block compression. Each frame is divided into 8 by 8 grids of pixels, a technique designed to conserve bandwidth by storing only the differences between blocks, rather than entire images. This process is efficient, but it also leaves fingerprints. Straight edges or sudden bursts of light can be exaggerated, sharpened into rigid patterns that may not exist in the original signal. That's the first line of explanation. Perhaps the sharpness of the glint was simply an artifact of compression, a ghost created by the codec itself. Analysts flagged that the bright streak aligned almost perfectly with several of these 8 by 8 borders, a sign that compression may have accentuated whatever faint feature was present. Under normal circumstances, this would be enough to close the case. But 3I/ATLAS was not normal. Another candidate is the ever-present threat of cosmic rays. High-energy particles race through space, and when they collide with a camera sensor, they leave behind a white-hot scar. These hits are typically fleeting, appearing for a single frame, then gone. In forensic analysis, they're textbook signatures. A bright line, a sudden dot, an anomaly lasting no longer than a blink. The anomaly in the 3I/ATLAS frame fits that description perfectly. One frame only, then silence. Some investigators argue that what appeared in the feed could easily have been a cosmic ray strike, subsequently sharpened by the codec's block compression into what looked like a straight edge. This double-hit theory, cosmic ray plus compression, offers a tidy, natural explanation. It's simple, it's plausible, it fits. But there is a wrinkle. The reflectance of the anomaly looked unusually consistent. Dust scatters light in diffuse, irregular streaks. Cosmic rays leave noise that is jagged, chaotic, sometimes too bright. Yet here, the glint behaves more like sunlight bouncing from a polished surface. Smooth, even, crisp, the kind of reflection that would make sense on a machined panel, but not on fractured ice. That tension between the ordinary explanations and the extraordinary impression is what keeps this frame in limbo. It is easy to say cosmic rays, it is easy to say compression. But when analysts stare at the data long enough, the question lingers. Why does it look so much like metal? The forensic breakdown closes no doors. Instead, it sharpens the stakes. If natural, it is an illusion of technology. If artificial, it is technology hidden in plain sight. The blackout. When the anomaly appeared, the signal that had been stable for hours suddenly dropped, leaving silence in its place. But here is where it fractures into two competing narratives, one grounded in official records and the other in whispers and claims. According to NASA's logs and the mirrored archives preserved by independent data watchers, the dropout lasted less than 2 seconds. It fits the profile of what engineers call a handover blank, a routine hiccup in the Tracking and Data Relay Satellite System, or TDRS. Signals beamed down from orbit often need to pass between satellites and ground stations, with the Deep Space Network coordinating the transitions. If a satellite dips behind Earth's curve or shifts out of range, the stream briefly disappears. Usually what you see on screen is a momentary pause or gray static. Then the picture returns. NASA's engineers pointed directly to this explanation. No manual override, no hidden command, just the geometry of satellites in motion. But another account reports that the public feed did not vanish for a heartbeat. It vanished for 3 full minutes. Not static, not compression streaks, but a clean blue screen. Viewers at home, who had been glued to the anomaly, sat staring at emptiness, refreshing browsers, asking each other if their connections had failed. And when the image finally returned, the comet had already shifted. The glint gone, the anomaly reduced to rumor. The discrepancy is striking. On one side, the official record that matches archived packet captures and server logs, a blip lasting under 2 seconds. On the other side, claims that the blackout was not technical at all, but deliberate, an intentional severing of the feed to prevent the world from seeing what came next. To some, the 2-second gap proves the system behaved exactly as expected. To others, the 3-minute cut is proof of a cover-up, a decision made in real time to cut away before artificial shifted from possibility to undeniable fact. It leaves the audience with a harder question. If the data shows both anomaly and blackout, then how do you separate the routine from the intentional? Data leading up to the cut. What makes the blackout more suspicious is what the instruments were recording in the minutes before the feed went dark. Comets are supposed to be dirty snowballs, water ice, rock, dust, and carbon compounds loosely bound together. But 3I/ATLAS refused to behave like a standard visitor. Spectroscopic readings showed a surprising abundance of nickel. Not just traces, but levels far above what any solar system comet had ever displayed. Nickel is a transition metal, heavy, and typically bound deep inside planetary cores or dense asteroids, not scattered loosely in a comet's coma. And the oddity did not remain static. As 3I/ATLAS approached the Sun, the nickel signal intensified as if the heat were activating something within the object, causing metallic elements to vaporize and shine in the ratios of elements hinted at alloys, combinations of metals blended together in proportions not commonly produced by natural processes. For those already primed by the anomalous frame, this data became the strongest argument for something engineered. To them, it was the chemical fingerprint of technology, not geology. There were other oddities. The coma, the diffuse atmosphere of gas and dust surrounding the nucleus, expanded to nearly 700,000 miles. an astonishing scale compared to the object's small, solid core. The discrepancy only fuels speculation. How could a body only a few hundred meters wide produce an atmosphere stretching wider than planets? Instruments also recorded that within the coma, dust waves oscillated at frequencies between 0 and 50 Hertz. Those numbers may sound unremarkable until you realize they overlap exactly with the range of human brain waves. Delta, theta, alpha, beta all fall within that band. Serious scientists spoke carefully, aware of the risk of sensationalism, but could not avoid noting the uncanny coincidence. Taken at face value, these readings make 3 I/ATLAS look less like a passive fragment of rock and ice and more like a system reacting dynamically to its environment. Heat triggers metallic emission. Plasma oscillates in structured ways. The coma expands beyond expectation. For skeptics, these are just the quirks of an interstellar body we do not fully understand. For others, they are footprints of something intentional, perhaps even designed. Important context tempers these claims. Other interstellar visitors have also broken the rules. Oumuamua accelerated without a visible tail, baffling observers in 2017. Borisov, discovered in 2019, displayed high carbon monoxide and even unusual nickel signatures, demonstrating that foreign comets can indeed defy our local norms. NASA's own analysis of Borisov confirmed that interstellar chemistry can surprise us, which means that while 3 I/ATLAS may look artificial, anomalies alone do not prove engineering. Still, the timing matters. Nickel spikes rising, hints of alloys emerging, plasma behavior straying into strange patterns, all recorded right before the feed cut away. The one frame of a razor-straight edge now sits against this background, and that makes the blackout feel less like coincidence and more like an interruption at the moment of maximum strangeness. The natural anomalies are explainable, but the pattern lingers, and the system's silence at that exact second feels a lot more than just coincidence. 3 I/ATLAS in context. To appreciate the weight of that question, it helps to understand exactly what 3 I/ATLAS is. This was not a homegrown comet born from the icy outskirts of our own solar system. It was the third confirmed interstellar visitor ever recorded. That alone made it precious. Interstellar objects do not return. They come once, pass through, and vanish into the dark, carrying secrets from star systems we may never reach. From the beginning, 3 I/ATLAS stood out. Spectroscopic studies showed its composition was dominated by carbon dioxide rather than water ice. Its coma and tail were powered by frozen carbon dioxide, sublimating as it approached the sun, producing jets and plumes far denser than expected. The coma itself was thick enough to obscure the nucleus, making direct size estimates difficult. Observations placed the core somewhere between 320 meters and 5.6 kilometers across, with most astronomers leaning toward the smaller end of the scale. That would make it comparable in size to 2 I/Borisov, and much smaller than a planetesimal. And yet, its dust halo ballooned so large that even the Hubble Space Telescope could not pierce it. What made this discovery particularly valuable is that ATLAS caught it early. Oumuamua was detected only after it had already slingshotted past the sun, giving astronomers just days to study it. Borisov, too, was a fleeting visitor. But 3 I/ATLAS was found with months to spare while it was still inbound. That meant a rare opportunity, a chance to watch an interstellar comet wake up as it heated, to track its chemistry, its structure, and its behavior as it passed through our system. All of the scientific context about the blackout makes the mystery sharper. Because if an engineered object ever did arrive from another star, this is exactly the kind of chance encounter in which we would find it, by accident, in a survey built for something else, preserved in a fleeting data set, seen once and never again. 3 paths forward. NASA's explanation was straightforward. It was a handover glitch, a dropout logged in the Deep Space Network records, a temporary lapse caused by orbital mechanics. Engineers pointed to the consistency of the signal fingerprints, to the identical gaps recorded across archives, to the absence of any manual override. On paper, the case was closed. But outside of the official channels, the explanations did not satisfy. Claims circulated that the blackout had not been accidental at all. Anonymous voices, speaking to forums and rumor sites, alleged that the feed was intentionally severed to keep the anomaly from the public. They argued that what had appeared in the minutes after the cut was too important, too disruptive, to allow unfiltered. Adding fuel to the fire were reports from amateur astronomers who said they observed unusual flares around 3I/ATLAS during the blackout window. These were not captured in the mirrored data, but they were recorded in field logs and social media posts. Whether the flares were real or misinterpreted atmospheric distortions is impossible to prove, but their timing made them part of the debate. If the professionals had gone silent, perhaps the amateurs had glimpsed what was missed. Meanwhile, official scientific papers on 3I/ATLAS focused on the comet's composition, orbit, and rapid disintegration. They were careful, rigorous, peer-reviewed, and entirely silent about the timing of the feed blackout. Nowhere in the literature does the word glint appear. Nowhere is the final frame acknowledged. For many outside observers, that silence looked less like discipline and more like omission. And so the controversy split along 2 lines. On one side were those who trusted the logs, who saw nothing more than a routine dropout magnified by coincidence. On the other were those who saw patterns in the omissions, who pointed to the absence of discussion in papers and the dismissal of amateur reports as proof that something had been buried. Caught in the middle were the archivists, the citizen scientists who had preserved the data in real time. For them, the event became a rallying cry for greater transparency. If not for their mirrors, the anomaly might have vanished into the archives, dismissed as a glitch without independent verification. Instead, the frame is preserved forever, immune to tampering, immune to erasure. They argued that this should become the standard: real-time mirrors, decentralized archives, open access that no single agency can redact or explain away. The blackout did not end the debate. It expanded it, turning a frame into a movement, a glitch into a question of trust. And once the question of trust enters the conversation, science and speculation begin to blur. Because once people start asking what else might have been hidden, the conversation is no longer about a single comet. It becomes about whether we ever truly see the whole sky. When all the evidence is laid out, the final frame, the verified archives, the blackout, the strange chemistry, the possible alloys, the plasma behavior, the trajectory, scientists and skeptics alike arrive at 3 broad explanations. Each has its advocates. Each has its weaknesses. The first and simplest explanation is that 3I/ATLAS was behaving exactly as a stressed interstellar comet should. Carbon dioxide jets, erupting as the body heated, fractured its nucleus. Those fractures exposed fresh faces of ice that gleamed sharply under sunlight. The torque from outgassing was strong enough to twist the nucleus, altering its spin by hours over weeks. Shards could have broken away, briefly presenting reflective surfaces. A fracture at the right angle, caught at the right moment, might look engineered, but be entirely natural. The second explanation sits in the machinery. Codec macroblocks can generate artificial straight lines. Cosmic ray strikes can produce bright one-frame streaks. Combine the two with a dust particle or background star in just the right position, and geometry emerges where none exists. This explanation is supported by the one-frame nature of the anomaly, consistent with cosmic ray hits. In this view, the anomaly is digital noise, nothing more. The third explanation is the most provocative. Spectral hints of alloy-like ratios, reflection crisp enough to resemble polished surfaces, a frame preserved across every archive, untampered, undeniable. If taken literally, the anomaly looks less like fractured ice and more like a fragment of something engineered. A probe, a relic, a message. If true, it would mark the first recorded evidence of an artificial interstellar object, the moment when speculation about extraterrestrial technology became data. These three paths are the fork in the road. None can yet be proven. Natural physics fits well, but cannot fully explain the crisp reflection. Artifacts explain the mechanics, but not the spectral peaks. Artificial origin is tantalizing, but demands a standard of proof far higher than one frame can deliver. Scientists demand more data, more confirmation across instruments. But the truth is this: the anomaly is real, preserved, mirrored, and verified. Its meaning, though, remains open. A blackout, etched in data. NASA's feed cut at 0317 UTC, and in that silence, the mystery of 3I/ATLAS was sealed. That evidence cannot be erased. Independent mirrors across the globe preserved it in perfect fidelity, untampered, unaltered, immune to revision. Scientists claim a fractured surface, a shard of ice glinting in sunlight. Others blame the machinery itself, compression artifacts sharpened by a cosmic ray. But the final path believes something far heavier, that the reflection belonged to a surface no comet should carry, a panel born not of geology, but of design. The truth remains suspended between those three roads. And one fact endures. NASA's feed, cut right after 3I/ATLAS, revealed something that should not have been there.